Okay, Physics 11H. Right now the video is a little washed out because I'm got the projector on here. I'm just got this on right now just to show you the two equations. I'm going to write the two experimental equations up in this area here, and then I'll turn off the board. But let me just pause this for a second. I gotta go grab a marker. Okay, so back with my marker. What you should be doing is taking notes on this, writing this evaluation of data down as if we were doing it in class right now. All right. I'm going to expect that you write down your own experimental equations on a scrap piece of paper so that when we come back to school, the next school day, I will check that off for remote day work points. So again, right now I'm a little dim because of this here, but when I turn this off, the light will adjust and it'll look better. All right, so our experimental equations. Again, I'm going to write them up here so that when we're done here, when I turn this off, you'll be able to see them nice. All right, so position versus time squared and velocity versus time. All right, so everything is in here. So position, you start with y equals mx plus b, then we plug in y, whatever the variable on the y-axis is, whatever the variable on the x-axis is, and then the numbers that this tells us in here. So let's go. So x is our y variable equals, and the slope of the line here is 0.9365. I can't tell it right there. 9365. I'm going to call it 0.94. We don't ever need more than 2 sig figs in this class. Okay. And the units on that are meters per second squared, because it's meters here, the units. The units on the x-axis are seconds squared. So meters per second squared, that's the slope of that fifth line. Now, the variable on the x-axis is a t squared. It can't put that into the fit line box just because of the format of it. It's a deficiency in the program. You didn't do anything wrong. In fact, in this box, it'll say x equals mx plus b. Well, you have to be smarter than the software. You have to know that the x variable is position, the y variable is time, t. It should be a lowercase x. They use a capital X in Logger Pro for some reason. Plus the y-intercept, which in this case is 0.093 meters. Basically zero, but you know, oh well, we'll see. 0.09, it's like 10 centimeters, so a little bit off, but not too much. That's our experimental equation for the position versus time graph. Now, you should put your numbers in here and here. All right? You shouldn't put mine in there. Those should be your numbers in there. Velocity versus time graph. It's x velocity, which just means the horizontal velocity, which is the velocity we're using. And so I know it's going to be a little bit hard to see this right now because of the projector being on, but in a second it'll be better. All right, the slope of this one is 1.6 meters per second times just t, because it's only time, it's not time squared, plus the y-intercept of 0.29 meters per second. Now this one I wrote a little bit larger so they could see it better. All right, so those are our two experimental equations. I'm going to shut this off now so that you can see the screen. Give the camera a second to readjust the light. All right, so now that looks a little bit better. It's refocused. You can see the two equations quite a bit better. X equals 0.94 meters per second squared times t, and V equals 1.6 meters per second times t plus 0.29. So we have two experimental equations going on. I'm actually going to move this one up here and analyze them side by side and give myself some room here. All right. V equals 1.6 meters per second t plus 0.29 meters per second. All right. So erase it here. We're going to go through this. All right, so now we got to determine what the slope and y-intercept mean here, okay? I'm going to start with velocity versus time because we've already talked about this a little bit. The slope of velocity versus time is defined as acceleration, the rate of change of acceleration, how much the acceleration changes by each second. So the slope of velocity versus time is what we call acceleration. All right, so this velocity is changing by 1.6 meters per second each second, and it's positive. So the acceleration of this car is 1.6 meters per second, or per 1.6 meters per second each second. So starts at rest after 1 second of moving, it's moving 1.6 meters per second. After 2 seconds of moving, it would be 3.2, 4.8, 5.6. So each second, it's going up by 1.6 meters per second. That is defined as acceleration. And the symbol we use for acceleration is a lowercase a. So that's the slope. All right, let's talk about what the y-intercept here is. Well, this would be if time was zero, it would be the velocity, right? The y-intercept, y-int, is the velocity when t equals 0. It's the value of the x-axis, or sorry, the y-axis, when the x-axis value is 0. Hopefully you can see this all okay in the video. I'll try to write it a little bit bigger here. All right? And we call that the, I'll do another bullet here, VI, the initial velocity going off the board. Initial velocity, okay? So, let's put that all together. So that's our experimental equation, right? This is our experimental equation. So that goes in your evaluation of data. Our final general equation running out of room here. Our final general equation, actually, I'm just going to erase this because, well, you can always go back. All right? So our final general equation here, we replace the numbers with the letters, the variables that we just defined. Okay, so the slope of the line is A T plus the initial. And that's our final general equation. Now, a supplemental exercise here is to take this and solve it for A, and we get an interesting result. So I'm going to solve this equation for A. So I bring the V initial over here, so it would be V minus the initial equals AT. Right? Then I divide both sides by T. I'm going to write it A equals V minus V initial over T. Well, that V, that so-called V, that is often what we call final velocity. And in fact, on the reference table, they call it VF, not just V. All right? So if A equals V final minus V initial over T, then that must mean it's equal to change in velocity over time. All right? So this equation is the general equation of this lab, but this equation is another useful one. It is simply this equation rearranged to solve for acceleration. All right, A looks kind of crazy, sorry. A equals delta V over T. All right. Now, one thing I just want to quick step back and talk about on the side here is, so you should write this down. It's good. I'm going to go ahead and erase this and talk a little bit more about the slope, the actual numeric slope. All right. So look at these units, meters per second per second. We don't really want to write that every time. It's important to think of acceleration as being amount of meters per second, but we don't want to write that every time. So what we in fact write, meters per second, right? How can we condense those down? Do the seconds cancel? No, they don't. This is like meters per second times 1 over seconds, right? So you actually end up with meters per second squared. All right, so a meter per second each second is equal to a meter per second squared. Right? Note this. Right? Let's talk about this equation now, your position versus time equation. That looks like acceleration, but it's not. This looks like the initial position, but it might not be. I'm just going to call it the initial position for now. It's the position x at t squared equal to 0. And I guess t squared equal to 0, that would mean that t is 0, right? So that is what we call our initial position. Great. That's usually what the y-intercept of these equations are. It's initial position, initial velocity, initial whatever it is we're working with. Now check out the slope of this line. Look at the units on it, right? Look at the units on it. It looks like an acceleration, meters per second squared. However, it's not the acceleration. This is 1.6, this is 1.94. Well, this data didn't come out that great. Some other cars, the data came out a lot better. This should be actually about 1/2 of the acceleration. So it ends up being about 1/2 of the car's acceleration, the slope of the position versus time graph. You know, that'd be 1.8, 1.9. This is 1.6. That's quite a bit off, right? 3 out of, 2. That's quite a bit off. So anyway, there's the bell. I have an engineering class coming in, but I'm going to quick wrap this up. The final general equation for this one is simply x equals 1/2 at squared plus x initial. All right?